So this is chapter 5, summarizing bivariate data, which means two variables. So let's start with an example. Suppose we found an age and weight for each person in the sample of 10 adults. Is there any relationship between the age and weight of these adults? For example, a 24-year-old in the sample weighed 256 pounds, a 30-year-old 124 pounds, and a 41-year-old, and so on. And so, is there a relationship? And if so, what do you think? If not, why not? So, a great way to visualize whether or not there's a relationship is to draw a scatter plot, which is just basically plotting each of these points as x and y coordinates on a graph. And so here's what the graph might look like. And if you look at the scatter here, there doesn't appear to be any real pattern there in the data. So suppose we found the height and weight now for each person in a sample of 10 adults. Is there any relationship between the height and weight of these adults? And if you do think there is, why? And if not, why not? And again, we'd want to plot a scatter plot to visualize if any relationship does exist. And so here's what the scatter plot looks like. And it looks like there is kind of a pattern here. It looks like as the height increases, one would expect the weight also increase. So it looks like it's just sort of a positive relationship there. And because they all kind of fall on a line, it looks like it might be a strong relationship. So the relationship between bivariate numerical variables, and this is the key here, they have to be numerical or quantitative when we talk about correlation, the correlation between two variables. These correlations may be positive or negative. In the previous example we just saw between height and weight, that was a positive relationship, and then it may be weak or strong. So that relationship in the previous example was kind of strong because all those points kind of roughly made a kind of a line. So this is now an example of positive. We look at an example of positive or negative relationships, no relationships, weak and strong relationships. So this set A, data set A, looks like it probably has a relationship. It looks like it's both strong and a positive linear relationship. Set B looks like there is little or no relationship in the data and two variables. Set C looks like there's a sort of a negative trend in the data there, but the relationship is not as strong as in set A. So it's a weaker relationship, and it's negatively linear. Set D looks like it shows to be strong, but instead of linear, it looks to be curvy linear. So you can see the pattern kind of curving right there. So we're going to identify some examples now as either having a positive relationship or a negative relationship or no relationship. So in example 1, heights of mothers and heights of their daughters. We probably expect that since height is genetic, there's a genetic aspect to it, there's probably a positive relationship. What about age of the car in years and the current value? Well, when the car gets older, most cars, they don't increase in value, they decrease, so we would expect a negative relationship. Weight of a person and calories consumed. Generally, the bigger a person, taller, they're going to eat more food to support their living cells, so that would be a positive relationship. What about the height of a person and a person's birth month? Probably not a relationship there. Doesn't matter what month you're born as far as how tall you are, so there's probably no relationship there. And the number of hours spent in safety training and the number of accidents that occur. Well, in general, the more you spend training, the more you're aware of potential hazards, and so you're more likely to probably have an accident, so there's probably a negative relationship there. And so we now look at a value called correlation coefficient, which I guess is kind of a way of measuring the strength and the direction of these relationships. So this would be the definition here for correlation coefficient, which we would symbolize as R. And so some keywords here is bivariate and quantitative. So the data has to be numerical. You can't have a correlation between one quantitative variable and one categorical value. That would not make sense. Pearson's is probably the most commonly used correlation coefficient. There are others. And it is used to estimate the population correlation coefficient given the Greek letter. You might recall some of the other population values or parameters are all symbolized with Greek letters, and then their estimates are given normal letters. So the statistic here that we would be using to estimate rho, the population correlation coefficient, would be the statistic here called the Pearson sample correlation coefficient. This is the actual equation for the correlation coefficient, and it looks a bit confusing, but you might recognize this here. This is an individual value, this is the average right here, and this is the standard deviation. In the previous chapter we learned that was called, those were z-values. So what are those called? Those are the z-scores. So these are z-scores for the x value and the y value for each individual observation. And so what this tells us is we're going to, for each individual value, we're going to record z-values or z-scores for both the x and the y variable for each individual. And we're going to multiply them, we're going to take the product of them, and after we do all that, we're going to sum them up. And then we're going to divide by n minus 1, which is the sample size, minus 1. And most calculators, by the way, will do that for you automatically, but it helps to know what the equation is. So we begin with, or we look at example 5.1. For the 6 primarily undergraduate universities in California with enrollments between 10,000 and 20,000, 6-year graduation rates Y and student-related expenditures per full-time student X for 2003 were reported as follows. So these are the values. So this would be the expenditures, and this would be the graduation rates. And what we would want to do with this for each of these, so each column represents a different university. So these are 1, 2, 3, 4, 5, 6 observations for 6 different institutions. And so we would go through plotting a scatter plot and then calculating R. We always want to start with a graph. So we would do the scatter plot, and it doesn't look like it's a very strong relationship. It looks like there might be a sort of a positive trend, but it's a whole lot of scatter there. If you actually calculate the R value, the correlation coefficient, you get 0.05. Okay, so how would we interpret that? What exactly does that mean, 0.05? So we're going to look at how you would do that. So here are some properties of R, the correlation coefficient. Okay, so the values can range between -1 and 1. Okay. If your R value is 0, that means there is no correlation, or at least not a linear relationship between the two. If your value for R ranges between -0.5 and 0.5, this would be a weak or moderate, weak to moderate correlation. 0.5 to 0.8 would be moderate correlation, and between 0.8 and 1, either negative or positive, would be strong correlations. Okay. So if we went back and looked at that 0.05, that would be a weak relationship. So now we ask the question, I got ahead of myself on the screen here, but here's the same data set, and suppose that the graduation rates were changed from percents to decimals by divided by 100. So we took and basically transformed these to decimals. What effect would that have? And then we see that it had no effect. So the R value is still the same. So this kind of demonstrates a property that when you do linear transformations on data, it doesn't affect R. R stays the same. We could actually transform both of these variables. And this is kind of important. For example, if you're collecting data on kilometers, for example, one of the variables, distance in kilometers, and you need to change it to meters, that wouldn't have any effect. It would be a linear transformation from kilometers to meters, and then you ran the correlation again, you would get the same value. Okay? So if you were to do the following transformations, indicated as prime that you've done something to the variable, and we transformed x by adding 14 and then multiplying by 5, and you transform y by adding 30 and dividing by 4, those are linear transformations. If you did that to this data set up here, you would still get, again, the same R value, or loop correlation, and the exact same value, 0.05. So what does this tell you about property of R? That it is not changed by linear transformations in these examples that we just showed. Now suppose we wanted to estimate the expenditures per student for a given graduation rates. In other words, we switch X and Y on our scatter plot. What happens to R? Well, R stays the same. Okay, so this is a third property here. The value of R does not depend on which of the two variables is labeled as X. Now suppose that one of our values here, this 33.9, was really 63.9. And so we ask what might happen to the value of the correlation coefficient. It's not that we would purposely change it, but what if that value instead was actually 63.9 in the real data set? And so we do a scatter plot again. I got ahead of myself, so let me back up a bit here. So this was the original scatter plot before the change. And what's going to happen here is, what if this value was actually 63.9? And so there's your new scatter plot. What did that do to R? R actually changed significant from weak to almost a moderate positive relationship. And the relationship does look a little stronger, except for this one data point way out here. So what does this tell us? That extreme values can affect the correlation coefficient. So that's something important to look out for. So value of R are affected by extreme values. Now it says, in this other example, find the correlation for these points. Again, we compute the correlation coefficient here, and we get a value of R. Does that mean that there is no relationship between the points? What it does mean, for sure, is that there's no linear relationship. Now, whether or not there isn't a relationship, that's where the importance of a scatter plot comes in. And so we look at the scatter plot, and we see there is actually a relationship here. That looks to be a curved linear relationship there. And so there is a definite relationship. It's just not linear. So this value shows, doesn't tell us anything about whether or not there's a relationship by itself. This is the importance of the scatter plot. So this example here shows the value of R as a measure of the extent to which X and Y are linearly related, not curvy linear. So recap of the properties of R. The legitimate values between -1 and 1. The values of R are not changed by any linear, should be linear transformation. Value of R does not depend on which of the two variables is labeled X. The value of R is affected by extreme values. And the value of R is a measure of the extent to which X and Y are linearly related. So, how do we, let's interpret now. So we're continuing with the example. So in order to interpret R, recall the definition of the correlation coefficient. And we can use that definition to actually interpret specifically within the context of this problem what that value means. So this was the definition for the correlation coefficient. It's a quantitative assessment of the strength and direction of the linear relationship between bivariate quantitative data. So if we look at the value here and these two variables here, and we want to write an interpretation of it, we would say that there is a weak but positive, because the value is positive, linear relationship between expenditures and graduation rate, and it's pretty weak. It's closer to 0 there. Okay. So does a value of r close to 1 or -1 mean that the change in one variable causes a change in the other variable? So if you were to get a 0.99 or 1 specifically, does that mean that x actually caused y? So let's look at the following examples. What if we did a study and we took a sample of individuals and we found that there's a relationship between the number of cavities in a child's teeth and the size of his vocabulary is strong and positive? Does that mean that one caused the other? I mean, would this suggest that we should feed children more candy to increase their vocabulary? Probably not. These variables are both strongly related to age of the child. Okay, so the point here meaning there was probably some other variable that we didn't control for, like age. Older a child, more cavities. Older a child, more vocabulary. The two variables being considered in the correlation were actually not, one was not causing the other one. Here's another one. Consumption of hot chocolate is negatively correlated to crime rate. Does that mean if you drink more chocolate, crime rate's going to go down? Probably not again. When it's very cold, people tend to stay inside and not get into trouble. They also drink. People who are cold and stay inside tend to drink chocolate, so it's probably chocolate not actually causing. So this brings up an important point, that just because you have a strong correlation between two variables does not show that one causes the other. There's not a causality there. Okay? The only way to do that is to actually do a well-designed and controlled experiment. In those cases, we can kind of eliminate some of these extraneous variables that we've talked about in previous chapters. For example, cold weather, chocolate, and crime rate. So, and we would tease out which variables are influencing our results.